attributes and transformations of cubic functions. So let's start by looking at the parent function, f of x equals x cubed. We'll graph it by making a t-table and finding some points. We'll choose some x values, -2, -1, 0, 1, 2. We'll find the output values by substituting in our input values. So -2 quantity cubed is -8. -1 quantity cubed is -1. 0 cubed is 0. 1 cubed is 1. And 2 cubed is 8. I'm plotting these points. We have -2, 8. We have -1, -1. We have 0, 0. We have 1, 1. We have 2, 8. And sketching in our curve, there is a graph of our parent cubic function. And from this graph, we can identify some of its attributes. We can see that the domain is all real numbers. It goes from -infinity to +infinity. The range is also all real numbers, going from -infinity to +infinity. The x-intercept is 0, 0, the origin, as well as the y-intercept is also 0, 0. And this cubic function has symmetry. It's not symmetric over the x-axis or the y-axis. Instead, we are symmetric about the point 0, 0, so we have rotational symmetry. If we were to rotate our graph 180 degrees, the graph would look identical to our starting graph. Okay, let's look at some transformations. So we'll start by looking at our parent function because we always want to compare it to our parent function. And then we'll have f of x equals 2x cubed, f of x equals 0.25 x cubed, and then we'll look at f of x equals -x cubed. So here we see all four of our graphs on the same coordinate plane. We have the parent function here in black. F of x equals 2x cubed is a vertical stretch, and we see it here in blue. F of x equals 0.25 x cubed is a vertical compression, and we see it here in red. And f of x equals -x cubed is a reflection over the x-axis, and we see it here in purple. In general, if we have y equals a times f of x, when the absolute value of a is greater than 1, we have a vertical stretch. When we have the absolute value of a is less than 1, we have a vertical compression. When a is less than 0, we have a reflection over the x-axis. Okay, let's look at another set of examples. Again, starting with the parent function, f of x equals x cubed. We'll also look at f of x equals x cubed plus 2, and f of x equals x cubed minus 4. So here's a graph of all three graphs on the same coordinate plane. We have the parent function here in black. F of x equals x cubed plus 2 is a vertical translation up 2 units, and we see that here in blue. F of x equals x cubed minus 4 is a vertical translation down 4 units, and we see it here in red. In general, if we have y equals f of x plus d, when d is positive or greater than 0, we are translating up d units. And when d is negative or less than 0, we are translating down d units. Okay, example 3, starting with our parent function, f of x equals x cubed. We'll also look at f of x equals x minus 3 in parentheses cubed, and f of x equals x plus 2 in parentheses cubed. Here are our three graphs on the same coordinate plane. The parent function is here in black. f of x equals x minus 3 quantity cubed is a translation right 3 units, and we see that here in blue. F of x equals x plus 2 quantity cubed is a translation left 2 units, and we see that here in red. And in general, if we have y equals f of x minus c, all in parentheses, if c is positive or greater than 0, we are translating right c units. Remember, c is following a minus. If c is less than 0, we are translating left c units. Okay, example 4, again starting by looking at the parent function, f of x equals x cubed. And then we'll look at f of x equals 1/2 x in parentheses cubed. And then we'll look at f of x equals negative 3x in parentheses cubed. So we have here, we see all the graphs of these three functions on the same coordinate plane. We have our parent function here in black. F of x equals 1/2 x cubed, we see here in blue. And f of x equals the opposite, or negative 3x in parentheses cubed, we see that here in red. In general, when we have y equals f of b of x in parentheses, when the absolute value of b is less than 1, like it was for our blue function and graph, then we have a horizontal stretch. And then when the absolute value of b is greater than 1, like it was in our red function, we have a horizontal compression. And when b is negative, or b is less than 0, we have a reflection over the y-axis. So let's look at some attributes of transformations of the cubic functions. So all cubic functions have a domain of all real numbers. So from negative infinity to positive infinity. All cubic functions have a range also of all real numbers, so negative infinity to positive infinity. All cubic functions have exactly one x-intercept. All cubic functions have exactly one y-intercept. And all cubic functions have rotational symmetry about a point. And our point would be the point C, D.